Mr. Abbott, time for another boring diagram explanation. This one comes from topic 8. It's number 61 on the bottom, and this one essentially is porosity, permeability, capillarity, and water retention. So we're starting off with two tubes. You'll see that those two tubes are filled with beads. The beads are sorted, which means they're all the same size and the same shape, at least within each sample. So you have equal volumes of two beads. You'll notice there is a drain valve on the bottom, and that drain valve is closed. If we were going to measure the porosity of these samples, what we would have to do is pour water between the spaces of the pores and see how much water it takes to fill the pores. If we did this, what you would discover, because they're both round sorted particles, for this one, the porosity of A and B would have the same porosity, and that would be about 40% because they're round sorted particles. If you change the shape, if you change the size, if you made them a mixture, if you put the small ones in with the large ones, that would reduce the porosity, but for the example that we have here, these two samples should have the exact same porosity. Now, to test the permeability is going to measure how fast, the rate at which the water flows through the samples. So you'd have to turn the drain valves and allow the water to pass through or infiltrate completely through the sample and collect the amount of water at the bottom. Now, it's much easier for water to flow through fewer large hole spaces or pores than it is through a lot of tiny little pores. This is going to have more friction. It's going to be in contact with more surface area. So tube B would definitely have the higher permeability. So for this one, B has a higher permeability. Honestly, it's easier for water to pass through large pore spaces. Now, if we were looking at the capillarity of these samples, capillarity describes the upward movement of the particles. Okay, you'd have to put the bottom of the tubes into a container of water and see how high the water gets drawn up between the pore spaces. In general, smaller particles have a much higher capillarity. So for this one, when you look at this, tube A would show a higher capillarity. That means the water would be drawn upwards a higher amount. Now, looking at the data that they gave us for these, one thing that they talk about is the water that remained around the beads after draining. The amount of water that you put in is not always the amount of water that you are going to get out. If you look at tube A, it said that 124 milliliters was put in to completely fill the beads. So there was 124 milliliters of water that it took to fill it. When you drained the beads, okay, there was 36 that was left around the beads. So if I took 124 and I subtracted the 36 that remained around the beads, that means when it drains, okay, 88 milliliters would be coming out. So if I do 88 plus 36, that's how I'm getting 124. So only 88 would come through. All right. Now, the question is, what do we call that amount of water that remains around the beads? Usually the term they're going to use for that is they're going to describe that as the water retention. If something is retained, it's left behind. So the water retention is the amount of water that sticks to the particles as water infiltrates or moves through the material. Now, how much sticks honestly depends on the amount of surface area. When you have smaller particles, an equal volume of small particles is going to have a greater surface area. If I had one particle that had square edges and each edge was 1 centimeter, the total external edges for the water to stick to, the perimeter of this would equal 4. Now, I take that same particle and I cut it into 4 even-sized pieces. Each edge of my new piece is going to be half of a centimeter. So I'd have 0.5, 0.5, 0.5, 0.5. I add those up and I get a perimeter of 2. So each one of these smaller particles has a perimeter of 2. I took one large particle with a perimeter of 4 and I cut it into 4 smaller particles. When I add 2, 4, 6, 8, the total perimeter now turns to 8. So smaller particles have more surface area, and the greater the surface area, the greater the water retention. So the water retention really depends on surface area, and we can see that smaller particles have more surface area. So if I was asked to predict what was going to happen for 2B, the water required to fill the pores is essentially asking you the porosity. That should be the same. So the porosity should have been 124 milliliters. The time required for draining isn't the permeability, but it depends on the permeability. As the permeability goes up, as it drains faster, the time should be reduced. So the 2B is going to have a higher permeability, so the time would have to be less than 2.1. Maybe it would be something like 1.6 seconds. Now, tube A, which has the smaller particles, retained 36 milliliters of water. Okay, the smaller particles have more surface area. When the water gets drained from tube B, less water is going to stick to the larger particles because, just like in our model over here, there's less surface area with fewer large particles than several smaller particles. So if this was 36, this might go down to 24. Okay, larger particles just don't retain as much moisture. Now, another thing that they can use in these diagrams, instead of giving you the exact size of the particle, they can use terms that we're going to use when we talk about stream velocity. So there are names for different size particles. You might think of sand as a material, as a specific substance, but honestly the phrase sand is telling you the size of that particle. So the place to find the definition for the particle size is actually on the chart on page 6 of the Earth Science Reference Table. It's got stream velocity on the bottom, particle diameter on the side. At this point, we're not even going to look at the graph. We just want to look at the scales over here. Okay, pebbles or particles. If I look at this, the smallest pebble is between 0.2 up to 6.4. So on my diagram, comparing these, a pebble is any particle greater than 0.2, but less than 6.4 centimeters in diameter. So pebbles are a wide range of particles. Now, there are two containers here that say they contain sand. Well, when I look at this chart, sand has to be between, if you're telling me it's sand, the largest sand grain is close to 0.2 centimeters. The smallest sand grain is close to 0.006 centimeters. Now, they've used qualifiers in here. This is coarse sand. If they say the word coarse, coarse means it's larger. It's closer to the upper end. If they use the word fine, fine means it's smaller. Okay? And sometimes they'll refer to the stuff in the middle as medium. Okay? So coarse sand here probably would be about 0.1 is slightly below. So that one might be 0.1 centimeters. For fine sand, if I look here, the labeled line, fine sand could be 0.01 centimeters. So there's a lot more sand grains of fine sand than coarse sand. Now, looking smaller than sand, what you get is silt. Silt is really tiny, fine particles. So when we're looking at silt, okay, silt has to be from 0.006 centimeters all the way down to 0.0004 centimeters. You don't have to memorize those numbers because they're honestly given to you right on this chart. Now, out of all of the particle sizes, clay is going to be the smallest size particle. The largest particles would be considered boulders. Boulders is anything that's above 25.6 or higher. Now, looking at these diagrams, okay, when you're looking at it, out of these, the pebbles would be the largest. So the pebbles would have the highest permeability. It would be easiest for water to pass through it. Out of these four columns, A, the one containing silt, is the smallest. So smaller particles on the smaller end, this would have a higher capillarity and water retention. Now, all of these are uniform particles. All of these are sorted. Okay, this is only silt-sized particles. So because all four samples are sorted, what you would see for these is they would have the same porosity. You could be asked, to alter the porosity. And one way that you could take these exact same materials and alter the porosity would be to mix them. So if you have a sorted sample, that means it's uniform size and shape. When things tend to be sorted, what happens is you've got more porosity, because sorted materials do not fit together all that well. Okay? The easiest way to reduce the space or to fill up the pores is to make it an unsorted sample. Unsorted would mean that's a mixture. The small ones would fit between the large ones, and unsorted particles are going to have a lower porosity and a lower permeability. The little particles clog up the pores for the big particles. So there's another set of diagrams that goes over porosity, permeability, capillarity, and water retention. We threw in a little bit about surface area. I hope this helps you understand the concepts.